this is what I would like to cover with you today. Actually, this topic is related to um, making connections between rational functions and real life problems. Because as far as you're concerned, I told you this many times that what we're studying here is not just simple um, math. It's math that used in the basics of physics, uh, chemistry, while describing natural processes that are happening. I believe it would be a great experience for you to see how it could be connected with some of the real life problems. For example, Boyle's law. This is going to be really interesting for us. Please let me know once you're ready to start the class, once you got all of your tags, copybooks, and we're gonna start with the first example. Please let me know if you're ready. Safa is ready. Everybody else? I'm waiting for yes in the group chat. Please, guys. Mohammed, Hala. Okay, great, great, great. Thank you. Thank you for that. So let's begin. According to Boyle's law, under constant temperature, the volume of gas varies inversely with the pressure. A tank holds 10 liters of hydrogen gas at a pressure of 500 kilopascals. Determine a function to relate volume and pressure for this gas. Okay, does anybody familiar with Boyle's law? It's quite interesting. There are three main laws for gases and their pressure. Main ratio expressed as P V pressure times volume over temperature. This is in first state, initial state, pressure, volume, and temperature equals to pressure at second stage, volume at second stage, and over temperature at second stage. This is the main relation for pressure, volume, and temperature, but Boyle's law, it's a specific form of this ratio where temperature is represented as a constant value, constant. So temperature does not changes from first state to the second one. So we can basically say that Boyle's law can be expressed in the following form. P1 V1 equals P2 V2, right? Take a notice that in this problem, we're not dealing with the temperature of the gas. We only said that we use the Boyle's law, and the temperature is constant. So question A, determine the function to relate volume and pressure for this gas. We found it. Question B, sketch a graph of this relation showing the volume of gas for different atmospheric pressures. So we're gonna start with making a coordinate axis as usual. Okay. If somebody of you can help me with that, I would be really grateful, because unfortunately my mouse is not functioning right now, so I have to use the touchpad. I would be really grateful if some of you can join me on the desk and help me sketching the coordinate axis. Is it possible? You can just use arrows, etc. Tell me if you can do that. Okay. Now, okay. So we're gonna start with sketch the graph of the flash showing the volume of gas for different atmospheric pressures. Okay, so let's say horizontal axis is gonna be the pressure, and vertical axis is gonna be volume, right? Why did I choose it that way? Because in this question, we're asked to show volume of gas for different atmospheric pressures. So basically, atmospheric pressure is going to be X, because it's going to be a variable for us, right? Different atmospheric pressure, and we test what volume would it have. So volume in this case would be Y value, dependent variable. Dependent variable, sorry. Does everybody agrees with me? Is it clear why I picked it that way? Great. So let's start with the simplest case, when the pressure and when the pressure equals 0. So first point, P1, we're gonna try is gonna be 0. In this case, volume of the gas according to this law. So if we're multiplying volume by pressure, if pressure is 0, volume, no matter what value volume takes, is gonna be the result of this ratio would be equal to 0. We don't know what volume is going to be when pressure equals 0. But we know that in our question, the volume of the tank is 10 liters, right? And this tank, it contained this 10 liters of hydrogen. Oh, sorry. Yeah, it's hydrogen. This tank would always contain 10 liters of hydrogen, right? But the result of multiplying pressure by volume would be different for different pressures. Is that clear? So in this case, volume equals 10 liters. Let me say volume is expressed in liters and pressure expressed in pascals. Oh, in pascals. So we're gonna sketch a graph of this relationship first of all. So first point of this graph, when volume is, let's say 10 would be here for us. It's 10 liters. And we change pressure. Pressure starts at 0. So first point, let me pick some other color for points. I suggest we use blue. So first point would be at 0, 0. This is going to be first point of the graph. Second point, I suggest we take pressure of 500 kilopascals. And let's make clarification here for convenience. Let's say coordinate axis of P gonna be expressed in kilopascals, not just in pascals, but in kilopascals. Like, so solvents. 500,000 pascals pressure. This is going to be our second point. What would you say? So 500,000 is going to be, let's say, somewhere here. So we have more, going to be 5, 0, 0. Second point, and result of this, if we multiply. Oh, okay. I want more. I have to fix this. I made a mistake. Actually, y-axis. Yeah, so I'm so sorry. Y-axis is not a volume. I made a mistake. And good thing nobody noticed it, because now I'll explain you why this is a mistake. Because our function is y value, right? FOP. That's what we have here. We have function f that is dependent on P, on pressure. We are asked showing the volume of gas for different atmospheric pressures. Function that depends on P. Just give me a second. No, wait. I'm sorry, just a second. Okay. So it's actually correct. vertical axis should be volume, because we need to show how volume changes with respect to pressure. But we forgot to notice one more thing, that P times V ratio, pressure times volume, supposed to be constant, right? Because that's a law. And we know that starting conditions is the tank holds 10 liters of hydrogen gas at a pressure of 500 kilopascals. So what we have to show that as P times V would always, this is always be constant value. This is also constant. Okay? P times V is also constant. P and V can change their values, but P times V is always constant. Great. I hope now it's clear. So first point, we cannot take it starting at 0, because it would mean that pressure equals 0, then the volume would have supposed to equal to 0. But in reality, pressure could never be equal to 0. It will approach some really small values close to 0, which would make volume change drastically. Okay? So we know that in our starting conditions, P times V, let me use it here, F of P equals V times P, and we know that it equals to 5,000. 5,000. 10 liters times 500 kilopascals. Let's keep it in kilopascals for convenience. Just remember that in order to bring it to pascals, you just need to multiply by 1,000. So this ratio gives us 5,000. So if, first point, let's say pressure would go as low as 1 kilopascal, then it means that the volume in this point should be equal to 5,000 divided by pressure, which is 1 kilopascal, which gives us volume of 5,000 liters. Okay? Does it make sense now? I think we figured it out. So when pressure, like somewhere really close here, like 1, then the volume would be an incredibly huge one, like 5,000 liters. I really want to make sure, guys, that you understand what I just did, because this is very important. Because I understand it now. I hope you understand it too. This would be our like starting point. Remember, this is gonna be basically an end behavior. We see as P approaches 0, because look, now we see why rational functions are involved here. Because P is in the denominator, right? So that means that P cannot be equal to 0, because if 0 is in denominator, we have the result is undefined. Is that right? Does everybody agree? Now we see why my first suggestion to put pressure equals to 0 is not correct. Guys, does anybody understand now? Thank you, Hala. Thank you, Mohammed. So moving on, for second point, let's say V2. We want a peak pressure equals so we know second point would be for us 10 liters and 500 kilopascals. Let's sketch the second point. I expect you to do the same thing in your copybooks with me and submit it as a part of your classwork. I'm going to open a folder at the end of the class. So this is our second point, and I suggest choose the third point as 500, 500, let's say 1,500. What would you say? 1, 5. So now pressure is 1,500 kilopascals. If we put this value into our ratio, we would have 5,000 divided by 1,500 kilopascals, which is equal to, does anybody has a calculator? Or you can do it in any way you prefer. 5,000 divided by 1,500. So I get a result as 3.3 in period. 3.3 and 3 in period. So I can say 3.3. 3.3, let's say it's somewhere here. 3.3. This, and joining crossroad of these 2 points, we're gonna get it right here. This is our third point. If you take even greater values, you're gonna see that volume gets as close as possible to 0. So now I already can sketch the graph of this relationship using these 3 points. It's basically sufficient to sketch rational functions in this case. Nice, like this. You see how you like this graph? I think it's beautiful. So first of all, let's state the domain and range of this function. So according to laws of physics, domain, which is pressure, equals to P E R. Pressure could take any rational number, and at the same time P greater than 0. Okay, pressure greater than 0. Pressure could be only positive and does not equals to 0. Range of this function, which is volume, also V E R, rational numbers, but pressure, volume greater than 0. Does it make sense? Because we cannot have negative volume, and also we cannot have volume of 0 if we had some initial gas in the tank. Does it make sense? Now you see why it's a rational function, basically. Any questions, guys?
Yeah, do you just want us to copy this down on our papers? Like what
Yes.
you...
Yeah, take your time. While you're doing that, I will explain you question C. What is the effect of doubling the pressure? Basically, as you can see, the relationship of volume and pressure is inverse. We divide by the pressure. So consequently, doubling the pressure, for example, multiplying pressure 2 by 2. Let me put it here. If we multiply the pressure by 2, it will reduce the volume 2 times. It will divide the volume 2 times. We're gonna have 2 times less volume. For example, if we had 500 kilopascals and 10 liters, 1000 kilopascals, 1000 kilopascals would give us how much liters? 5 liters? No, it's even, yeah, 5 liters. 1000 kilopascals will give us 5 liters. Same way, if we had 5000 liters with 1 kilopascal, with 2 kilopascals, we're gonna have 2500 liters. Let me know once you finish copying this down. Okay, great guys. Good job. I'm gonna clean the desk now. I want you guys to answer this question on the desk. D. What pressure value will give a volume of 2.5 liters? As we did with volume with respect to pressure, now just show me the inverse relationship. How would the pressure change with respect to volume? Remember that ratio is P, V. Please, each one of you write on the desk your answer. 1 for Safa, 2 for Hana, and 3 for Muhammad. Show me how you solve it, please, guys. And then we're gonna have a 15 minutes break for you. Guys, I just want to make sure you understood your tasks for now. Show me how you find inverse relationship of volume with respect to pressure, and what would be the pressure for 2.5 liters. Okay, is it clear? So basically what we know that P times V should be equal to 5,000, right? That's what we figured out at the beginning. 5,000. Now to show how pressure changes with respect to volume, pressure equals 5,000 divided by volume. We know that the volume for this scenario is 2.5 liters. So 5,000 divided by 2.5. 5,000 divided by 2.5 equals 2,000. Great job. Who gave the first answer? 2,000 kilopascal. Hala. You did it? Safa. But Hala sent me a direct message. You both did a great job, Safa and Hala. You both get an extra mark for that. I appreciate it. You actually send it simultaneously in direct messages at 1750 exactly. Good job, girls. I appreciate you. I appreciate your efforts. Mohammed, do you understand why 2,000 kilopascals is the right answer now? Great. Good job, guys. So I'm gonna clear the desk. And let's take a look at example number 2. The time taken by a water pump to empty a pool is inversely proportional to the rate of pumping. Write an equation representing the situation using a constant of proportionality. I want you to take a moment to think about this. Here, room for Safa. Here, room for Hala. Here, room for Muhammad on the left. Please, I want to see your reasoning. How would you solve this problem? And then I'll get back to you within 10 minutes. And we're gonna do it together, right? I'm gonna tell you my reasoning about it. I want you to learn how to work on your own. The time taken by water pump to empty a pool is inversely proportional to the rate of pumping. So let's say rate of pumping is RP. I don't know. You gotta choose your own the notation. Rate of pumping. What is rate of pumping? Is number of pumps. How do we represent rate? Number of pumps with respect to time, right? How many pumps we did in what time period? Do you agree with me? Please do the next steps. You have some time, and then I'll do it with you. Okay? Okay, guys, we have a first answer from Hala, from Mohammed too. Let's see. So Hala, T equals square time taken to empty the pool, a rate of pumping, constant of proportionality. Great, Hala. Value of constant proportionality would be 40,000. I use the equation T equals CR time rate of pumping C constant. Pump takes 40 minutes to empty a water tank and a rate of 10 liters a minute. What will be the value of constant of proportionality? Okay, great job, Hala. Value of constant proportionality would be 40,000. I use the equation TCR. Great job. Yeah, absolutely right. So we know that function for the time that it takes to empty the pool would be time equals constant of proportionality divided by the rate of pumping, right? Great. Knowing that, constant of proportionality would be equal to time that it takes to empty the pool times the pumping rate, which would be equal to 40,000. Great job. And then replacing a water pump with 1,500 liter minute pumping rate, how long will it take to empty the pool? So basically what we see here is that the pumping rate, which was 1,000, now increased by 500, or in another word, is multiplied by 1.5, right? Which means time that it takes to empty the pool, if it was 40 minutes before, time should be divided by 1.5. And 40 minutes divided by 1.5, how much is it gonna be? 40 divided by 1.5 is 26.6 minutes. Or what else could we do? We could divide 40,000 by 1,500. Yeah, 26.6 and yeah, many in period. So 26.67. And finally, we have to sketch the graph of this function using appropriate variables on the axis and appropriate domain and range. Well, what can we tell about domain and range for this function? I would say it's exactly this. It should be similar to what we did just before, right? Because for x value, what would be the independent variable? It would be pumping rate. So pumping rate would be the domain of this function. So pumping rate greater than 0, and range of this function, time that it takes to empty the pool, should be greater than 0 as well, right? Domain and range is similar to what we just did before. And if we were to sketch this graph, we would see that it looks exactly the same as the one we had before. It would be something like this. But you just need to find 3 points that you're gonna sketch through. Is that clear? Guys, any questions about this problem? Can we move on to the next one? Great job, guys. I appreciate it. And let's move on to example number 3. The maximum time t in minutes a scuba diver can rise without stopping for decompression on the way up to the surface is defined by the equation. Time with respect to distance. Oh, with respect, sorry. Time with respect to depth, 525 constant ratio, divided by d minus 10. d is greater than 10, our domain. D is the depth of the dive in meters. For maximum time to be less than 30 minutes, how deep can the diver dive? So basically what this says to us that we have certain restrictions on the range of the function. Because maximum time should be less than 30 minutes. So time should be greater than 0 and less than 30, right? This is our range restrictions. How deep can the diver dive? So I suggest we find how deep should the diver dive in order for time to be 30 minutes. So in case for 30 minutes, we have a ratio of 30 equals 525 divided by d minus 10, right? We know that d is greater than 10. That's a requirement, even according to this notation, because denominator cannot be equal to 0. Next step. So what we can see here. Let's find the depth from this equation. In order to do that, I will perform simple mathematical operation. I'll multiply left and right hand side by d minus 10. d minus 10 equals 525. 525. Now we need to open the brackets. 30d minus 300 equals 525. Now we move 300 to the right hand side. Be 825. And on the left hand side, it's gonna be 30d. Now 825 divided by 30 is 27.5. So 27.5 meters. Basically, so at the depth of 27.5 meters, the maximum time the scuba diver can rise without stopping for decompression is 30 minutes. So for any depths less than for any depths greater than 27.5 meters, decompression maximum time to raise without decompression would be less than 30 minutes. So 27.55 meters would already have less maximum time for decompression. Is that clear? Do you get my reasoning about this? Any questions, guys? And obviously, to sketch this graph, you would see, first of all, depths greater than 10. So it's going to be past this line. Depth is greater than 10. And also time is going to be from 0 to 30. And the greater the depth, the less time for decompression can be, then less time the diver can raise without decompression, the greater the depth is. So the ratio should look like this. So initial graph would look like this, right? But we're interested in only this region because this is when time less than 30 minutes. So we would say as soon as when depth is 27.5, somewhere here, this is where the graph would cross this upper border. So starting from here, graph would look something like this. Is that clear, guys? Please make sure to copy this into your copybooks. No? Mohammed, ask your question, what you don't understand. That was 2 minutes ago. Yeah, basically the greater the depth is, then less time diver can elevate himself in water without stopping for decompression. The deeper you go into the sea, the more frequently you have to stop for decompression, right? Then the time is shorter, time becomes smaller. In all of the three examples that we discovered today, the ratio is as follows. It's going to be a descending ratio. And you can see that for every one of them, solution looked like this. This is a classic rational function. In the previous classes, we had more complicated forms that may look like this, but because in this class we connected them to the real life situations, we don't have a solution for negative numbers. So the curve isn't a negative. What does it mean? What does it mean curve negative? I don't understand. Curve has negative rate of change going down. So decreasing. Function is decreasing with respect to the x variable. Graph on the graph. I don't really understand what you say. So what I was trying to explain you that in the question it says time supposed to be less than 30 minutes. So we have upper border for time, right? If there would not be upper border, you would see that the less the depth is, the longer the diver can raise in the water without stopping for decompression. You see, for example, for being 10 meters, for being like 15 meters down into the sea, it's 500 divided by 525 divided by 5 would be 105. So it means diver could uh, go up for 105 minutes without decompression. But you understand that when you're 15 meters deep into the water, you won't spend 105 minutes to raise up. So basically, that's why I think they apply this limitation, less than 30 minutes. Because after you get to the certain depth, for example, let's say 27.5 meters, it's going to take you some time to go up. And you would like to do it slowly because if you go up fast, pressure is just gonna damage you. That's why we have this upper limit, level left side limit of 10 meters, at least 10 meters deep. And the deeper you go, the more frequently you have to stop for decompression. If you would knew that some of the divers, they even have special submarines following them. So when they finish diving, they stop in those submarines for decompression. They enter the submarine and they stay there for they could stay there for a day, and they're getting slowly and slowly elevated from the bottom of the sea or the ocean, because otherwise they wouldn't survive this operation. Написал? Okay, guys, if you don't have any questions, I suggest we finish earlier so you have time to do your home assignment. And yeah, thank you for participating in class today. It was a great working with you together. I'll post the home assignment now so you have some extra time to do it, okay? Thank you guys, appreciate it, and see you soon. Have a good day and a good evening, and see you on Sunday. Thank you guys. Bye bye.